Okay, we'll go from current slide. All right, volleyball schedule. Today, the 18th, I think it is, isn't it? Yeah. Our volleyball team is facing Southern Union, hosting them in Birmingham, 5 o'clock this afternoon. So if you can get over there, I'll be over there, but I'll be teaching a class, so I won't get to see it. Then tomorrow, that's Thursday, they're going to Fayette, Alabama to play Bevel State at 6 p.m. So if you happen to be up that way, I don't know exactly where Fayette is, but it's somewhere around. They play at 6 there. And then over the weekend, Friday, Saturday, they have a tournament in LaGrange, Georgia, and they don't know the times of those matches yet. And then next week we'll get into those. All right, and by the way, our volleyball team had the best season ever, I think. Last season they had won more matches than they had ever won in the history of the program. So they're.
Who are they playing on with LaGrange?
It's just a tournament over there, so I'm sure it's some of the schools from Georgia and I guess LaGrange College there is a college there, so they're probably playing them and several other area schools. College Scholar Bowls is currently recruiting players with knowledge in any subject, including history, literature, science, music, current events, mythology, mathematics, you name it. Mr. West is the coach. He's on this campus most of the time. He has classes on the other campus too, but his office is down the half flight of stairs. The first classroom on the left is 259. The next one, 261. His office is in between those two classrooms on the left. There's not a number on his office door. All right, so that's College Bowl. And the exhibition at the Birmingham West Campus Library, survivors through Alabama Holocaust survivors through photography and art. This will be going through, I think it's next Tuesday, September 23rd. So that's in the library over there. The program they had was last Monday, so that's over with, but the art exhibit is still there. And the NASA's Community College Aerospace Scholars Program is still receiving applications for this year up through October the 16th. So if you want to participate in that or know of anyone who does, there's that. All right. Now, we did this slide, I'm pretty sure, last time. Any questions before I get started today? Okay. What's that?
I think.
Okay. Well, if you come up with any, we can stop them anytime. We did this slide last time, I'm almost certain. No, we didn't. The slide above it we did. Okay. This is 12.18. Okay. This is where we start today. In many projectile problems, the constant vectors R0 and V0 are not given explicitly. Okay? R0 being the initial position and V0 being the initial velocity. Okay? Often you're given an initial height, which would be, basically you can get R0 from that, and initial speed, magnitude of V0. Okay? Not the vector V0. That's what they're doing. They're distinguishing between the scalar quantities you're given, H rather than R0, but that's really easy to do. But they give you the scalar quantity, the speed V0, not the vector V sub 0. Well, here's Josh, I bet. Yes. Okay. Okay. We're just saying a lot of times they don't, in projectile problems, they don't give you the initial position vector. They may only give you the height, which is real easy to get from that. Okay? You and they don't usually give you the initial velocity vector. Most of the time they don't. What they give you is initial speed, okay? And maybe the angle at which the projectile is launched. If they give you that, you can come up with the velocity vector. Because if you know the speed, which is the length of the hypotenuse, so to speak, then, and the angle here, then you can split this into component form, and the sine of this angle is going to be your y value, right? Oh, I'm sorry. The sine of the angle is the y value over the hypotenuse, which is y over v0, your speed. So your y is v0 times the sine of the angle in between. And your cosine of this angle is the adjacent side over the hypotenuse, which is the x component divided by the initial speed. So the x component of the speed is going to be v0 times the cosine of the angle theta. So that's how we get the x and y components, and from there you can put together a vector. Okay. So that's what they're getting at, I think. Let's see where they go with that. For a given height, you can deduce that the R0 is the height times j, because height is vertical, j. Because the speed gives the magnitude of the initial velocity, it follows that speed is equal to magnitude of your initial velocity, which you don't know. So you can write the initial velocity as xi plus yj. And from what we just saw, the xi is that magnitude that you do know. So why do they keep putting this in here? V0, not the vector V0. V0 is speed times cosine theta I plus V0, the speed, not the vector magnitude, sine theta j. That gives it to you. There you have it. So, don't know why they keep putting this in. If this is what's given, this is how you get it. They give you the initial velocity and the angle at which it's fired, which is usually what they give. Then you can write this down, and if they give you the initial height, then that's a height, so then that's hj. Those are r vector. So that takes care of those pretty easily. So the position vector can be written then, r of t is equal to minus 1/2 gt squared j, okay? That's always your acceleration is minus 1/2 gt squared j, plus t times v0, but v0 you can give from this, what we had before, the speed times cosine of the angle I plus t times the cosine of the sine of the angle j, the speed times the sine of the angle j, plus your r, which is just your hj. So, if you split that up in components, your only component in the positive x direction is your t, well, they write it this way, v0 cosine theta, that's what they gave you, times ti, that's your initial velocity in the horizontal direction, and then your initial height, h0, plus v0 sine theta, that's your initial velocity component vertically, times t, minus 1/2 gt squared. And that's then j component. This is your horizontal velocity. There's your vertical velocity. Okay? Well, I mean, not velocity, displacement. Horizontal displacement, vertical displacement. You factor out a t, you get the velocity. Horizontal and vertical displacement. So here's theorem 12.3, which came from that. Neglecting air resistance, which is sometimes not a good thing to do, but most of the time we will, for low enough speeds, that's not a bad idea to do. For neglecting air resistance, the path of a projectile launched from an initial height h with an initial speed v0 at an angle of elevation theta, described by the vector function. This is exactly what we got. The horizontal component is just that velocity in the horizontal component direction, v0 cosine theta times t. The time at which, how long it's been going at that velocity, because that's constant. It's not changing. So whatever the time is, that's how far you've gone in that direction. Plus, now this one changes because you've got initial height here, your initial velocity component vertically, but being reduced by the acceleration pulling it down, that then gives you your displacement in the j direction. Where g is the acceleration due to gravity, right there. We usually use 9.8 in the SI system, 32 or 32.2 in the U.S. customary system. All right. So here's example 6. A baseball is hit 3 feet above the ground. Does that make sense? 3 feet above the ground is about waist high, okay? And good sweet spot to hit the baseball. About 3 feet above the ground. So guess what? There's your initial position. That's where the baseball was, 3 feet above the ground. At 100 feet per second. I don't think I can do that, but let's say you can. 100 feet per second, that is the speed at which you hit the baseball at an angle of 45 degrees, good angle to choose, with respect to the ground, as shown in this figure here, okay? Find the maximum height reached by the baseball, and frankly, who cares? But they do want us to find the maximum height reached by the baseball, okay? All right. Now, how do we figure out what the maximum height reached by the baseball is? You hit it here, it's going up here. How do you determine what's the maximum height? When the
velocity.
Yeah, the vertical velocity is here. Absolutely. Okay. So what was our vertical velocity? My pen is all wrapped up here. Okay, that is the I've got to sneeze, sorry. I don't know why, but okay, maybe it'll stop. There, I doubt it, but let me try. Whoa. All right. All right. This is your total velocity. That's, if I can use that's your V0 here. And that's your 100 feet per second. Okay? Now, your horizontal component of that would be here, and your vertical component would be here. The horizontal component has nothing to do with how high the baseball is going. That's strictly horizontal. It's this component, okay? Well, what is that vertical component? Let's call that V sub y is equal to it's related to what trig function? Sine. Sine of 45 is equal to the opposite side, which is your V sub y, over to your hypotenuse, which is V sub 0. So the V sub y is equal to V0 times the sine of 45 degrees. Goodness gracious. What is the sine of 45 degrees? Exactly. So this will be V0, let's see, root 2 V0 over 2. 1/2 root, yeah, whatever, however you want to say it. Okay? Now, we want to know when that total velocity, when that initial velocity, vertical velocity, goes to zero. What's dragging down on it? Gravity. So when this, and what in the world do I have written there? That's supposed to be a zero there. All right. There is no V2, V0. Okay. So when this is equal to 1/2 g t squared, no, that's displacement, 1/2 gt, that will be where your, because, okay, acceleration due to gravity is straight down. G is minus G, okay? I don't need the 1/2 in there, sorry about that. All right. The speed in any time is, if you take the derivative, let's phrase it this way. Acceleration is dv dt, okay, is equal to minus g, right? That's your component of acceleration, only being pulled down by gravity. So if you write this as dv, well, dv is equal to minus g dt, and then integrate both sides, you get v is equal to minus gt, possibly plus the constant. But if initial velocity is zero, then that's going to be okay too. Well, no, that's not what I meant. Initial, let's just leave it like that. Okay, it's minus gt. Now, so your total velocity of the ball is this minus that, and if you move that to the other side, set these equal to, that will be at time t equal to root 2 v0 divided by 2g, okay, because you're going to divide by sides of 2. That gives you the time when the maximum, when your velocity is 0, okay? The time when the velocity is 0. So what you do is plug in and see what time that is. Your initial velocity is 100 feet, so 100 feet per second divided by 2 will be 50 feet per second, okay? And then divide that by, well, you got a root 2, we'll fiddle with that in a minute. Divide this by 32 feet per second squared. Okay, the feet are going to go out, and one of the times is going to go out, or seconds is going to go out, and that leaves you 1 over second, so that's going to give you second. That's going to be the time. So what time does that turn out being? 50 root 2 over 32. So someone with a calculator punch that in. You can simplify that a little bit. 25 root 2 over 16 if you wanted to. But whatever. What would be that time that it reaches 0 velocity? Zero vertical velocity. Vertical velocity. 25 root 2 over 16. Anyone got it?
On the long hand, It's 2.137.
Say that again.
Is it 2.137?
2.127, is that what you said?
137.
Huh, 137?
Yeah.
Okay, 137.
Is that close enough?
I don't know. I haven't done it. I don't have a calculator up here. They say 2.21.
Okay.
25 root 2 divided by 16, which is what I got, and they say 21.21. I mean 2.21. Now I don't know. I haven't done it, so I don't know. 2.21 seconds. All right, that gives you the time where it says maximum height. What we have to do is figure out what the maximum height is now. And from our last formula we had, remember the height, the J part, was H0T plus V0 sine theta T, okay, minus 1/2 GT squared. This is the H sub Y at any time T, right? Vertical height at any time T. If you go back a slide, here it is. H plus V0 sine theta T minus 1/2 GT squared. I think that's exactly what I've got there. Okay. Okay. Now wait. I'm sorry, I put an extra T in here. I knew something looked strange here because height isn't multiplied by time. Okay. Height, the initial height plus how much it rose because of the initial velocity minus how much it fell in that same time interval due to gravity. Okay, here is where you plug in your 2.21 seconds for your time. I'm not about to do that. I know it's 3 feet. I can do that part. Plus 100. Well, we've already done that. So it's 50 root 2. No, wait. 50 divided. Yeah. We just done that calculation before. 50 root 2 over 2. No, wait. Okay. 50 root 2. It's 100 root 2 over 2. So that would be 50 root 2 times your 2.21. Okay. Minus 1/2. And here we're going to use 32 times 2.21 squared. All right, that should give us our maximum height. 3, which is your initial height, plus the amount it went up due to the initial velocity, that's your 50 root 2 times t, 2.21 seconds. That was 50 root 2 feet per second times second. And then the 1/2 of 32, which I can do that. 16 times 2 root 2 squared. So if you can punch those numbers in and see what you get. Three plus 50 root 2 times 2.21 minus 16 times 2.21 squared. Well, does no one have a calculator? If you don't sweat it. I'm sorry. I thought someone would have a calculator. Doing what it says here, and why they calculated what it was, and then went back and put the whole numbers in again, I don't know. It's about 81 feet. Now, why you're worried about how high it goes, I don't know, okay? In case there's any low-flying birds, are you going to hit them? I don't know, okay? The odds are not, okay? Now, that's the first part of the problem. Find the maximum height of the baseball. But then the next part is, will it clear a 10-foot high fence located 300 feet from home plate? Okay? So the first answer is 81 feet. Okay. Now the second answer, second question, will it clear a 10-foot high fence located 300 feet from home plate? Okay. Well, here's sort of a key to this one. Okay. You're 300 feet from home plate, and guess what never changes in this problem? Your horizontal component of your velocity. That doesn't change. It's going to be the same forever. Okay? So, that will...
Do you want the height? Was 10 feet off the ground, that plane?
Say that one.
Do you want to find the height?
Yeah. Yeah.
When it's 10 feet off the ground.
Right.
You may get two answers there, but you want the one over here.
Yeah, exactly. But, okay, you're saying take that and set it equal to 10?
Yeah.
Yeah, that will certainly work. See, but you see, you still, that will give you a solution for time, right? Well, that doesn't tell you will it clear it or not. That, you see, you still don't have time. You got everything else, and you're seeing if it'll be 10 feet. That would give you 2 times, and then you still got to say, well, are either of those times reasonable? One won't be, it'll be a negative number. The other time, maybe. So I'm saying let's do that first, okay? Since we know now, I think here is where it was. No, that wasn't where it was. I thought we did it. Maybe I've already erased it. Okay, we know the horizontal component, maybe we did. The horizontal component of velocity does not change. So V sub x is going to be V0 times the cosine of 45 degrees. Okay? Now, so that means, and we know what cosine of 45 is, and this thing times the time is going to be your x displacement, how far it's going to go. Well, we want it to go 300 feet. So let's say 300 feet is equal to this thing. Let's see what time it'll get there. So 300 divided by this, which is very similar to what we did before. This would be 100 times root 2 over 2. That would be 50 root 2. That's the V0 times the cosine of 45. Because cosine of 45 is the same as sine of 45. Okay. Divide that. See, is that divided by or divided into? Divided into. Okay. Divide that into 300. Okay. Sorry. All right. 4.24 or 4.2? Which did you say?
4.24.
Okay, good. Okay. This will be 4.24 seconds. Okay, that's how long it's going to take the ball to go 300 feet. Right? Plug this in here and see what the height will be then. Okay? So plug it in, plug it in. If that's, did I write it down? Yeah, 4.24 seconds. Plug it in here. That's 3 plus, this is your 50 root 2 times 4.24. Now, if y'all don't have a calculator, don't do this by hand. Minus this times that. This is 16 times this thing squared. See what you get. I almost guarantee you it's going to be greater than 10 feet. Okay? Because I've worked this problem from a different viewpoint and a different class. I think they use the same, I know they use the same angle, I think they use the same velocity, and I believe they were still 300 feet. In his pre-calculus class, he did the same thing, except gave you a different formula. And
That's a little over 15.
yeah, it came out 15? Okay, yeah, okay. What, you do have a calculator?
I got one on.
Yeah, okay. I was hoping you did, but. Oh, I see, okay. It gave 15 feet, okay? And even the tallest, best jumping center fielder, if he got over there, and even if he was trying to climb the wall, I don't think he'll reach 15 feet, okay? So I think that's a home run, okay? Unless that's a foul ball. I didn't check on that, okay? All right.
Doesn't give you that angle.
Yeah, it didn't give you that angle, so it will clear the fence. Whether it's in fair territory or not, it looks like it would be fair territory, but that's just looking at it. All right, so 15 feet. Good deal. That's the last problem in 12.3. Oh, let's see how they finish it. So let's just go to the next slide. You're given that h is equal to 3, v0 is equal to 100, theta is equal to 45. That was what was given. Using the theorem 12.3, with g is equal to 32 feet per second, that produces the r of t is 100 cosine pi force. Why did they change to radians? I'm not sure. You know, it works just as well for 45. Okay. Plus 3 plus 100 sine of pi force t minus 16. There they did the 1/2 of 32. Minus 16 t squared. Okay? That's your formula for your displacement. Now, and that gives you 50 root 2 t I plus 3 plus 50 root 2 t minus 16 t squared j. So they just calculated the sine and cosine of pi force. The velocity vector then is your first derivative of that, which I did it the other way, taking the integral of your acceleration, and that gives you 50 root 2 I plus 50 root 2 minus 32 t j. Okay. It's your velocity vector. Notice your velocity in the x direction is constant. Velocity in the y direction starts off constantly being pulled down by your acceleration. Okay? The maximum height occurs when the y prime is equal to that. When y prime is equal to the unit in here. In other words, when that goes to 0. Okay? And that goes to 0 when t is equal to, exactly like we figured, 25 root 2 over 16, which was 2.21 seconds. Okay. So the maximum height is reached when the ball is at that height, which is 3 plus 50 root 2 times 25 root 2 over 16 minus 16 times 25 root 2 squared. Okay. and that's 649 over 8, which would be right at 81, approximately 81 feet. The maximum height when t is equal to 2.21 seconds. Okay. Now, when the ball is 300 feet from where it was hit, the h of t is equal to, x of t is equal to 300. So that means your 50 root 2 t is 300. When you divide that, you get t equal 4.24 seconds, just like you got before. I didn't do it that way, but you certainly can. Divide both sides by 50 and you get root 2t is equal to 6, right? And divide by root, let's see, 6 divided by root 2, t is equal to 6 divided by root 2, multiply numerator and denominator by root 2, your denominator becomes a 2, 2 will go into 6 3 times, so 3 root 2, which is 4.24 seconds, which is what we got. At that time, the height of the ball is given by your y component, 3 plus 50 root 2 times this. Why in the world? Okay. They really do get a correct answer this way because now you're not rounding any here. That becomes a 2. So it'd be 2 times 3 is 6 times this plus 6 plus 300. And then minus that. And when you square that, you get 9 times 2 times 6. So you can work all that out in your brain almost, and that's 303 minus 288, which is 15. Therefore, it does clear the 10-foot fence, and it's not a foul ball, it's a home run. They told us that. I know you were worried about that. Okay. Now, that is the last slide in the section, so homework here is any of the odds 3 through 9. They're all at Calc Chat. 3's at Calc View. I'll leave that up if you need to see it. Whoa, that's not what I wanted. Well, it's too late now. I don't think it'll let me. Okay, so how could I discharge? I thought I was going back a slide, but it didn't. All right, I guess I clicked anything and it exited. So any of the odds 3 through 9, they're all at Calc Chat, 3's at Calc View. Any of the odds 11 through 19, they're all at Calc Chat, 15's at Calc View. Any of the odds 21 to 25, they're all at Calc Chat, 21's at Calc View. Any of the odds 27 to 39, they're all at Calc Chat. Okay, got to find where that goes to there. Then do 41, it should be at Calc Chat. 43 should be at Calc Chat. 45 should be at Calc Chat. Then they introduce some circular motion. So either 47 or 49 could be worked. This circular motion formula they give you. Sorry. Then do number 51. It should be at Calc Chat. 53 and 55 you can think about or explore doing those. I don't know if there's anything actually to calculate there. It's just thinking through them. The answer should be at Calc Chat. 57 should be at Calc Chat, and 59 is a proof. If you want to do that, you certainly can. And 61 and 63 are both proofs. Any questions? 12.3. So let's go on to 12.4. Well, doesn't seem to be wanting to open. It's coming now, I think. Here we go. All right. Slideshow, current slide. All right, now I don't know if you recall, but we just had, I think, this picture and that picture in the last section. I think some of the others may have been earlier. But that doesn't matter. We're still on vector value functions. 12.4 is tangent vectors and normal vectors. Okay? Our objectives here is to find the unit tangent vector. What does that mean? Unit tangent vector.
Vector in tangent.
It's tangent to the curve.
In unit form.
No, magnitude of 1. That's what we mean by unit vector. Magnitude of 1. So, any old vector tangent to the thing is a tangent vector. The unit is the one that has a magnitude of 1. And a principal unit normal vector at a point on a space curve. Now, we'll do this later, so I don't want to get too bogged down with it now, but a tangent vector is obvious. So if your curve's like this, tangent vector's like that, the normal vector will always be perpendicular to the tangent vector, and the principal unit vector will be one this way and one this way. The one that's toward the inside of the curve, that's the principal unit normal vector. The one pointing outside the curve is the other. Okay, so that's at a point on the space curve. We'll find the tangential and normal components of the acceleration based on those unit vectors, tangential and normal unit vectors. Okay, so the velocity vector always points in the direction of the motion, and it's always tangent to the point where you're measuring that. Okay, this observation leads to the next definition, which applies to any smooth curve, not just to those for which the parameter represents time. So it doesn't have to be talking about time here. We're talking about, here they talk about velocity vectors, that would be time, but there is a unit tangent vector, okay, or a tangent vector, which it doesn't have to be, the parameter doesn't have to represent time, okay. The definition of a unit tangent vector, let C be that smooth curve. Now, smooth curves means they're continuous, and there's no angles, joints, cusps, corners, anything like that. It has to be smooth. Let C be a smooth curve represented by the vector R on some open interval I of whatever your parametric variable is. The unit tangent vector. Now, they capitalize it for tangent vector, but they don't have any way of saying that's a unit vector. It is. When you see that capital T, they mean a unit tangent vector. When I do it, I put a caret on it, a housetop looking thing on it, to let you know. So the unit tangent vector is, of course, got to be in the direction of the, has to be in the direction of the first derivative, okay, because that's tangent to the curve, okay? So it has to be in that direction, but it needs magnitude of 1, so divide by its magnitude. And that makes a tangent vector that's a unit vector that's tangent to the curve. Now that's as long as that r prime of t is not 0. If that's a 0 vector, you don't have a unit tangent vector, okay? Because if the r prime of t was 0, the magnitude of that would be 0, and you're dividing, so that just doesn't work. In other words, if you're not going at a speed, you don't have
a tangent.
Yeah, exactly. We know that the curve is smooth on an interval when r prime is continuous and non-zero on that interval. R prime is continuous and non-zero on the interval. So smoothness is sufficient to guarantee the curve has a unit tangent vector, because this will always be the case if it's a smooth curve. All right, so let's do it. Find the unit tangent vector to the curve given by r of t is equal to ti, let me get my pen back, oops, ti plus t squared j, when t is equal to 1. So how are we going to find the unit tangent vector? What's one thing we got to do? Take a derivative. R, since I don't write in bold, I'll put the arrow over it. R prime of t is equal to I plus 2tj. Got it. All right, once you've taken the derivative, now you can plug in the t is equal to 1. You could calculate the unit tangent vector as a function of time and then plug in the 1. But once you've got that, you're okay to do it. So what will this be? R prime of 1. What would that be? Okay. Wait, it's still a vector. Yeah, you're jumping ahead to the velocity, but we'll get there. 2j, right? I plus 2j. Okay. Now we want the unit vector that's in that direction. So that's what we divide by the square root of square root of 5. Perfect. Okay. So there's the unit tangent vector to the curve at that place. Now, you could write it this way if you wanted to. There's a couple ways. 1 over root 5 I plus 2 over root 5 j. Now, you could put root 5s over 5s in both of those places if you wanted to, but this is just as good. Now, let's just check and make sure that's a unit vector. What's this squared? What is that squared? 1/5 plus 4, which is 1. So, yeah, that's the unit vector. 5/5, which is 1. So that's a unit vector, and it's in the direction of the tangent vector at the value t is equal to 1. Okay. I think that's all we had to do on that. Let's see. They left it close to what I had to begin with. Oh, and they write it this way. Once you do that, once you divide by the magnitude of r prime of 1, that gives you your unit tangent vector, which I write like this. This is at 1, not at t. Okay. So they wrote it almost the same way I did. They wrote it as unit tangent vector at 1 is equal to 1 over root 5 times I plus 2j. Okay. Now, I don't know if you recognize that curve, but if you wrote that parametrically, you might say, this thing, this basically is saying y is equal to x squared, which is your good old parabola. This is t equal 1. There would be your slope and everything else. So let's see if they'll draw it for me so I don't have to draw it myself. Okay. Let me clear what I've written here so you can follow it. The derivative of RT is equal to R prime of T is I plus 2TJ, exactly like y'all said. So the unit tangent vector is R prime over R magnitude, prime of R magnitude. The magnitude of R prime, that's the best way to say it. And here they plugged in the whole thing. Now, I don't think it was necessary, but you could. excuse me. The magnitude part here is, this part down here is the square root of 1 plus 4t squared. Okay, so it's 1 over that. It's this thing over that. R prime of t is this over this, and this is the scalar part. There's basically your vector part, and then when you do it t equal 1, the first part here becomes root 5, and the next part becomes 1 plus I plus 2j, which is 1 over the magnitude times the vector itself. Okay. Now, yeah, thank you for the picture here. It's a good old parabola. Okay. Y is equal to x squared, just like what they call it, a parrot function. At 1, 1, there's your vector, your tangent vector, and then divide that by the magnitude of the velocity vector, of whatever that vector is, and you get unit tangent vector. Yeah. Unit tangent vector, you don't believe it, they're trying to draw it so its length is unit length. Okay. The R prime was probably much greater than that. It was I plus 2j. That would be I this way, 2j that way would be here. That would have been a much longer vector. You divide by its magnitude, you get unit tangent. Okay. Now, the tangent line to a curve at a point is the line that passes through that point and is parallel to the unit tangent vector. Well, kind of a backward way of saying it, because the tangent line to a curve, that's where we started to get our unit tangent vector. So, yeah, parallel to the unit tangent vector. In example 2, the unit tangent vector is used to find the tangent line at a certain point on a helix. So now we go into 3 space. Helix, you can't do that in 2 space. That's going to be a 3 space problem. Okay, so here comes example 2. First, we're going to find the unit tangent vector, and then find a set of parametric equations for the tangent line to the helix given by this form. R of t is equal to 2 cosine t I plus 2 sine t j plus tk. Okay? At the point root 2 pi fourths. Okay, hold on a moment. Let's just make sure this is this point is indeed on this curve. Okay? Let's start with t is equal to pi fourths. Okay? The sine of pi fourths is root 2 over 2. Multiply that by 2 and you get root 2. So there's your j component. Your k component was pi fourths. Your j component was root 2. Your I component, or your x component here, would be square root of 2 over 2 times 2. The 2's cancel out, so you get square root of 2 over 2. Yes, this is consistent. This point is on that curve. Okay? So once you convince yourself it was, then we're looking for the unit tangent vector, and then a set of parametric equations for a tangent line to the helix here, given by that point, or at that point here. Okay? So, parametric equations for the tangent line. Okay. So we got to find that unit tangent vector. How do we do that? First thing we do, take a derivative. Good choice. Okay. And what will that be?
-2 sine of t
Okay.
plus 2 cosine t plus k.
Plus k. Good. Okay. It's an ugly sign, but let's see if we can make it look a little better. Okay, that looks a little better. All right. That's a tangent vector, first derivative, but it's not a unit tangent vector. How do we get the unit tangent vector? Yes, that this vector, minus 2 sine ti plus 2 cosine tj plus k divided by its magnitude. What would be its magnitude? 4 sine squared t plus 4 cosine squared t plus 1 square root of that. That would be the magnitude squared, so you take a square root of it. All right. All right, now folks, it's at this point, what is your t? Pi over 4. There it is right there. Okay, that gave it away. So the unit tangent vector, I was just making sure that's what we want now. I'm pretty sure it is. At pi fourths. And what would that be? Anybody? What's the sine of pi fourths? Minus 2, because it'd be root 2 over 2, so I think it's minus root 2, right?
Yeah, that's what I said.
Oh, I didn't hear the root. Minus root 2i. Root 2j. I can't write a j. Okay, let me get that written better. Plus k. All right, divided by the square root of 2 plus 2 plus 1 minus root 2 over root 5 I plus root 2 over root 5 j plus 1 over root 5 k. Oh, I'm sorry. Wait. We found t of t. That's what we're looking for. Okay? They didn't ask for they didn't ask for the unit tangent vector at that point. They asked for a set of parametric equations for the tangent line to the helix given by this r at this point. Okay, so what we wrote here is fine, but it's not a set of parametric equations, I don't think. Okay, well, let's see what we got. Let's just make sure we did it right. This squared would be, no, okay, 2 over 5, right? Plus 2/5 is 4/5 plus 1/5 is 1. So yeah, that is a unit tangent vector at that point, but I don't think that's what they're asking for. Then find the set of parametric equations for the tangent line to the helix given by, this is the helix, so we want the tangent line given by that. Okay. All right.
Looks like they just saw the bottom, like the magnitude.
Oh yeah, I didn't turn the page, so I'm not looking at that. Okay. Actually, they did the very thing I did. Okay. I guess they were doing. This would be, and they just pulled out the 1 over root 5. And they said that's minus root 2i plus root 2j plus k. Okay. They just pulled out that. They did do that function there. It didn't tell them they had to, but it did it. Okay? Now, but I guess they do. Now it says using the direction numbers, if you remember how we write the parametric equations for a line, you need these direction numbers, and where you get those are these right here, that, and that. Okay? You could put them over root 5, but they're just direction numbers, so you don't have to put them over that. They're perfectly happy just those direction numbers. Okay? And the point in question is this point right here. Okay? So your parametric equations, and they're using parameter S, and there's no real reason not to use it. Well, yeah, I guess there is one. Not to use a t, because you've got t's already here. And if you use the t as your parameter, you'd be getting those two t's crossed up. So to keep it from being confusing like that, let's go with the new parameter s. Okay? Now, the set of parametric equation would be s, x is equal to, it would be this one, which is root 2, plus this direction thing, which actually would be a minus. Oops, we erased too much. Minus root 2i, not root 2s. We don't need the unit vectors that. It's root 2s. That's an ugly S, so I'm going to go and erase it. In fact, the book doesn't write it this way, but I like to write the S in front. That way there's no confusion about whether the S is inside or not, inside the radical or not. Your Y value will be your root 2, that's from the point here, plus S root 2, and your Z value, what are you doing here? Okay. For some reason my pen quit operating, and it's still not operating. There it is. And Z is equal to pi fourths I think I put a circle there, but it's a 1K plus S. Okay, I believe that's your parametric equations. Yeah. Now they write the S afterwards, which, as long as you're really careful, you can do that. But I like to do root 2 minus root 2s. They did root 2s. I put s root 2. Y is equal to root 2 plus s root 2. okay? Because there's, you might be tempted to think that S is under the radical, it's not. And then Z is equal to 1/4 plus S, because you're, oh, I was writing on it with the wrong pen. The coefficient there is 1, so it's just plus. All right. All right, let's erase all this and watch how they do it. The derivative of r, of course, is r prime, which is minus 2 sine t I plus 2 cosine t j plus k, which is implies that the magnitude of that is root 5, just like y'all did. Now, they did it before. They did it with the t still in there, and that certainly works, because sine squared t plus cosine squared t is 1. You have a common factor of 4 here. 4 times 1 is 4, plus 1 is 5. So it's another way to do it. Therefore, the unit tangent vector is a tangent vector, r prime, that you had there, minus 2 blah, 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 divided by the magnitude of r prime, which is root 5. So that gives you 1 over root 5, pull the magnitude out, and then minus 2 sine t I plus 2 sine t j plus k. Gracious, I'm stiff. Okay, and that's the same thing we got there, yeah. Okay. Now, at that point, this point, root 2 5/4. That's where we're doing the tangent line, at that point. The t is obviously 5/4 because it was, you know, a cosine something I, sine something j, plus dk. So the t had to be 5/4. And the unit vector, which they didn't say we had to calculate, but we did, and that is 1 over root 5. And then you plug in pi-4 here, and that's root 2 over 2. Pi-4 here is root 2 over 2. And then you just got k here. So minus 2 root 2 over 2 plus 2 root 2 over 2 plus k. The 2's cancel out in both cases. Minus 2i plus minus root 2i plus root 2j plus k. That's your direction numbers. Now, you could write that over the root 5 or not. Doesn't matter. They're your direction numbers is what they call them. Okay? So, this is how you write that when you cancel out the 2's. Yeah, I forgot that we're going to do that. Okay? Using the direction numbers that you got from here, A is minus root 2, B is root 2, and C is 1. You don't have to carry around the root 5, you know, just any multiple of that. That's the most convenient multiple. Okay? And the point being, at the point of your intersection, which is your root 2 pi-4, you can obtain the parametric equations given with the parameter s. Don't use t because that was already in the problem. So it's x sub 1 plus 8s. This is your x sub 1. This is your a. So it would be root 2 minus root 2s. Most of the time, these are not going to be the same value. That just makes this problem seem sort of trivial, but it really isn't. That's root 2 minus root 2s. And then your y is going to be your y1, this root 2, plus s root 2. So root 2 plus root 2s. And this is fine as long as it's clear that the radical ends there and the s is outside. I just like to write it the other way, because my writing is not always clear. And the Z1 here is the pi fourths plus the C here is the 1. So it just be pi fourths plus S. All right. So there were the parametric equations you were looking for. Now, that tangent line then is shown here. Here is the helix in question. It started at t equals 0 here. So that was a 2, 0, 0. T is equal to 0. This will be 2, that's 0, and that's 0. So we started here, and then as you went up over here, you were at 0 for x, so you're right above the y-axis, and this would have been plus 2 j, so you'd be right over that point, plus pi fourths k. Okay? And then you just keep going around the helix. Okay. Now,
I'll bring a tin can in so we can move around.
yeah. Just imagine you're taking a strip off a tin can and you're doing it very gently.
Yeah, but I'll say to you, bring a tin can so we can trace it out.
Yeah. Yeah. I may have a Coke can down in the office, which might be able to do. Here's the point, pi fourths in, so you go on the pi fourths, that's halfway, you're at splitting the xy here. Go up here, you're root 2, same values, x and y from here, and pi fourths is your t here. That's how far you are above that plane. That would be about 3/4 of the way up, so somewhere about right there. And then to get this tangent line, what you do, what's the necessary part, you have these points, and what you do is use the unit tangent vector, which gives those direction angles. Now, the thing that I don't want to make a big deal about it, but yeah, I guess you had to plug in the T. I was going to say, is there a reason you did? Because you didn't use all the T. You just, all the angle. You just used the parts of it. You just use this part. You could have put it over this, over this, over that, but that wouldn't have gained you anything except extra writing. You still would have had the same parametric equations here. You would just have a root 5 underneath the those. So I don't think it made any real difference there. Okay. Now, in example 2 that we just did, there are infinitely many vectors that are orthogonal to the unit tangent vector. Okay? I said 2 before, but there's an infinite number. One of these is a vector that's t prime of t. Okay? And why is that true? Well, t dotted with itself is the magnitude of t squared. Okay? But we know what the magnitude of t. This is a unit vector, and the magnitude of a unit vector is 1, and you square that and you get 1. So, they then suddenly say that's true. Well, why is that true? If you were to do the product rule of this, you would get this dotted with this the derivative of this. So unit tangent vector dotted with the derivative of the unit tangent vector plus the same thing twice, okay? And that's equal to derivative of this is 0 because this is 0, okay? It has no t thing. So therefore you can divide by 2 and find out, yeah, indeed, the unit tangent vector and its first derivative, they're orthogonal to each other, okay? That's all this tells you, because the dot product is 0. So by normalizing this, now what do they mean by normalizing?
Negative symbol of it.
No, okay. Yeah, you divide by its magnitude. In other words, you make it a unit vector. See, just because this is a unit vector, that doesn't mean this is a unit vector too. In fact, it probably isn't. But once you found out that, you know it's perpendicular to it, you normalize that by dividing by its magnitude, making it a magnitude of 1, 2. Okay? You obtain a special vector called the principal unit normal vector. There are many vectors orthogonal to t. Let's go back. Here is that unit tangent vector would be right here. Okay? Unit 1. Okay? Perpendicular to that could be pointed inward, outward, upward, downward. You know, anything perpendicular to that, there's an infinite number of vectors that are. But the one that we're talking about there is the one that's pointing inside the curve. Well, I think you'll see it later better. Okay. If you take the derivative of that, normalize it, it's going to be pointing inside that curve, and that's the principal normal vector. Okay? So here's your definition. C is a smooth curve represented by R on an open interval I. Okay? If t prime of t is not equal to 0, it can't be 0. When you take the derivative of that unit tangent vector, it can't be 0. Okay? And as long as it's not, then the principal unit normal vector at that same value t is defined as t prime at that value t divided by the magnitude of t prime at that value t. That makes this a unit vector as well. And it's a unit vector, they'll tell you later, pointing toward the inside of the curve. Okay? So, how we doing time-wise? We got time. So let's try it. Find n of t and n of 1 for the curve represented by this. Okay, so this is going to be two-dimensional, I think. Okay? What do we have to do first? Take the derivative of this. R prime of t is equal to 3i 4tj. Then what do we do?
Magnitude.
Take the magnitude of that. R prime of t is equal to the square root of 9 plus t squared. Got it. Then what do we do? Yes, and that gives you the unit tangent vector as a function of t, and that's equal to, probably the easy way to write it is like this: 1 over root 9 plus 16 t squared times 3i plus 4 tj. Okay? It's this divided by that. Okay? Now what? Okay? Now here's a big boo hiss. Take the derivative of that. Because you're looking for the unit tangent vector. The unit tangent vector is the derivative of that, divided by its magnitude. So it gets really messy really quickly. because now you've got t's in the numerator and denominator. Okay? So I'm beginning to rethink what I just said, and I think I will, well, let me not erase it. Okay. I'm going to write it this way. 3 over the square root of 9 plus 16t squared, I, plus 4t over the square root of 9 plus 16t squared, j. All right, so now I want to take the derivative of this thing. Unit vector t prime. Okay, now here's where I run into problems. I don't want to make this confusing, so I'm not going to call that a unit vector. T was a unit vector, and we're taking the derivative of that, but its derivative won't be a unit vector, so I'm going to go on and put the vector symbol back in there, okay? Not the unit vector symbol, just to keep from being confusing. So we've got to take a derivative of that, and what will that be? I think I'm going to even rewrite this again. 3 times 9 plus 16t squared to the minus 1/2 I plus 4t times 9 plus 16t squared to the minus 1/2 j. Okay, that's easier to take a derivative of. Not a lot, but some. What does that become?
Negative 3 over 2 times 9 plus 16 squared times 32t.
32t. Oh, wait, you left something off here.
Oh, negative
3 halves, right. Times 32t I. Okay? Whoa, this one's a little bit worse because it's a product rule. How do you do that? I said we could easily get this done. I may have been mistaken.
We got a 4t times.
4t, you said?
Yeah, well,
Okay, yeah, that's fine. It's fine. Yeah. 4t times
negative 1/2 9 plus 16t squared to the negative 3 over 2 times 32t.
okay. Plus
30. Wait.
Oh, this is the easy part.
Plus 9.
Okay, let's do the 4 first.
Okay.
You don't have to, but just so I won't forget about it.
Then just it's not easy to say those.
No, okay. All right. The chain rule with okay. Now, I wish I had more room. Okay. All right, let's get rid of what we can. The 2 will go into 32 16 times, so this will be a minus 48 over 9 plus 16t squared to the 3 halves. I don't know if it's any easier to write it that way, but it takes up a little less horizontal room. Okay. All right, now let's see what we got here. I think I want to do the plus first, if you don't mind. So I'm going to do plus, and that would be 4 over 9 plus 16t squared to the 1/2. minus, because that's going to have a minus in it, and that I believe is 64t squared. Over 9 plus 16t squared to the 3/2 j. Now, I'll look at this and I'll say there's got to be a better way. Okay? And we are almost there for the better way. Okay? Notice they all have, not make it time wise, but let's try.
That second,
Yeah.
64t squared over that.
Yeah. If we pulled out of all this your the radicals in the denominator. Let me just make sure I haven't botched up something here. Okay. What they do, clever them, is pull out the parts with the 3/2 from the part with the 1/2. Okay? So here's what they've got, and this is a weird way to do it, but it works. The first root of the unit tangent vector, let's pull out that 1/2, and that's going to be a j. So that's going to be okay, and that's just going to be a 4j. Okay, now pull out, oh, it's going to be a minus because both of those are minuses, aren't they? I sure hope they are. They look like it to me. And again, let's pull out the 1 over 9 plus 16t squared to the 3/2. And what we've got here is a 48, I'm sorry, 48i. I believe it is. I've lost where I am there. Yeah. We've already pulled out the minus sign. 48i plus, because we pulled out the minus sign for this too, 64 t squared j. Now, obviously 48 and 64 have a common factor. What would that be? 8 would certainly work. Is that what they got? They say actually got a little bit more 12. Is that right?
Yeah.
12 will work. No, 12 won't work, will it? Or 16.
Yeah.
Yeah, 16 will work. So if you pull out a 16, and I just don't have enough room to write here, again, this will be 1 over 9 plus 16t squared to the 1/2 times a 4j minus 16 over 9 plus 16t squared to the 3/2 times 3i plus 4j. Okay, I wondered how in the world they got that, but that's what they did. Okay.
Honestly, I probably would have just left it the way it was at the bottom.
Yeah.
And then when they told me what t needed to equal,
Yeah, that would be far easier if we go on and plug in the 1.
nightmare.
Yeah, If we'd plugged in the 1, that would have been hunky-dory. But they wanted n of t.
Oh, okay.
Okay, and that's why we're having to leave the t's in there. Now, what they do now, and unfortunately I don't have room, and I don't think we have time, but what they're going to do is get this over the 3 halves power 2, which means you have to multiply by a 9 plus 16t squared here in the numerator, and then make this a 3 in the denominator. 3 halves in the denominator. Okay? Oh, I should have done it here. Sorry. 9 plus 16t squared up here, and make this a 3 halves down here. And now combine all those things together, and it really does turn into an enormous, it seems like it's a bad mess, but it really doesn't turn out as badly as you would think. But that just gives you t, the unit tangent vector prime. Then you've got to take the magnitude of that, which is another effort in futility. Okay? If you follow in your book, you'll see that. And as Bill objects to this, he skips steps like crazy getting there. It makes it look so simple to do that, and then divide by that. And the surprising thing is you come up with something pretty amazingly simple. Okay? And I'll write it here for you because we don't have room to derive it. That because your magnitude of that comes out fairly simple. Let me write that down. The magnitude of that t prime of t okay. He does this. Why am I writing all this? Let me just erase all mine and let show you all the skip steps. Okay. You differentiate first, which we did. The magnitude was that. Okay. Unit tangent vector was that, which came out being this. Now, this is the part that is not entirely clear. Oh, no, that was exactly what we got. That's the unit tangent vector. Now we take the derivative of that, which he is skipping lots of steps here, but this is exactly pretty much what we came up with. I put the 4 up here and the j out here, and we had separated that out. Now I didn't pull out the t. I probably should have. That would have made things a little easier, I think. But at that stage, it looks bad enough. But, somewhat simple. Okay?
That's why I got this big question mark.
Yeah.
Where did they get that from?
Yeah.
Okay, I'll go back now.
Yeah. Where we left over when we were doing it, we were awfully close to this. I think I erased it, so I can't go back and show it. Sorry. Yeah, I had to erase it so I could see what was being written here. Sorry about that. Okay. But we got the 3i. I think I even had the t in there now that I think about it. I don't know if I had the t up there. But anyway, now he's going to multiply by the, he doesn't even show that. Oh, man.
I can understand the negative part, but I was trying to go back and look at this. Where was the negative from the start, so it's minus thing, the product. I just couldn't come up with it.
Yeah. Here is a quantum leaps of steps here. Because it changes from a 3i here to a minus 4ti here. And the reason is you multiply this by why he changes his notation, I don't know. Multiply this by 9 plus 16t squared in the numerator, and that makes a 9 plus 16t squared to the 3/2 power here. Okay? And that's times the 4j. So then you have to multiply the 4 times all this, and the 4tj times all this, and manipulate around like crazy. And other things factor out, and somehow you came up with the only term you have with the I in it is this one, right here. And it changes from a 3 times 16, which is 4, and this will be a minus 48, so that works. Yeah, so this does, that's still consistent here. And what is the amazing thing is that your j's, you have a 16t squared here, and you're going to have a multiple of 16t squared here, 4 times 16t squared here, and that's takes way more time than we have now to work all these out. But if you did do that, yeah, we were very, very close to this. We just hadn't gotten this part yet. That's where I just was running out of room. Okay, now that gives you UT prime. Now you've got to divide by its magnitude. And that's another thing. So here's the magnitude of this. When you square this, you're going to get to the 3rd power. Well, that's just
the easiest.
Again, you're going to have a lot of cancellations to get to this point. You've got to, because this part stays the same, and this will be 16t squared plus 9 again. So you're dividing by that yet again, the square root of 16, 9 plus 16t squared, and the square root of that. And when you multiply by that, you get the 3rd is, but then you still got a square root in here. It seems like he has an extra square root left over. Another big question mark here. How do you get to that? And then, when you divide this by that, well, the 12s go out. These go out. And you're just left with that in the denominator. And sure enough, this is in the denominator. For the life of me, it looks like this square root sign shouldn't be there. Because otherwise, then this would come out exactly like what we're supposed to get. And this is your magnitude of this. Okay? No, I'm sorry. Don't divide yet.
Well, take the square root away.
Yeah, take the square root away and you got it. Yeah. Because this is to the, this is to the 1/2 power, this is the 3/2 power. That will be to the 2/2 power, take the square root away and you just got that. That's exactly right. Okay. So this does, as long as this is correct, that comes out to be that. And this is what you divide into this. Well, if you divide this into, this divided by this will be, this will be a 1/2 left down here. This goes away completely. So you get this thing right here. There's your thing to the 1/2 power here, and exactly what we had there. This thing right here was there. Minus 4ti plus 3j divided by, that's the 1/2 power. That's the principal unit volume vector. Okay. I think we're way out of time, aren't we? Yeah, sorry about that. And that's just the first half of it. Now you just have to plug in a 1. T is equal to 1. That's the easy part. Okay. Plug in the 1 and you get 1/5, because that had to be 25 over 4i minus 4i plus 3j. Okay. Now, use your unit tangent vector at the same place, and here's something to note. This and this, and these are both unit vectors now, okay, evaluated at 1. So if you'll notice, if you did a dot product of these, forget about the 1/5, they would take care of themselves. But this would be a minus 12 plus 12 is 0, perpendicular. These are always perpendicular to each other. So once we found this, if we had done this first, we could have just flipped these two.
Oh, whatever makes it equal to
Right,
0.
equal to 0. Yeah.
Well, that's what I was saying. I would wish he would give us one of those, say, 1 plus 3 up here, and let's go down to a minus 1 over 3 down here.
Yeah,
Before he did all that.
Yeah, but this just shows that indeed
Well,
you
this
get that.
seems like just a straight application of physics.
Right, exactly. So let me, boy, it looks like here is an understatement, and this is where we'll begin next time. The principal unit vector can be difficult to evaluate algebraically.
Yes.
What an understatement we have there, okay? And that's where we'll begin next time. Okay.
Yeah, we're kind of doing this in my physics class, except
What's that?
we're kind of doing the same thing in my physics class.
Oh, I
except
see.
It's like 10 times easier.
Right. Physics cuts through the crap. Sometimes,
Yeah.
it just gets to the place. Homework exercises here. I think you can do any of the odds 3 through 7. They're all at Calc Chat. 5's at Calc View. Any of the odds 9 through 13. They're all at Calc Chat. 9's at Calc View. Try doing any of the odds 15 through 19. They're all at Calc Chat. 15's at Calc View. And we'll stop there and pick up the rest of those next time. All right, any questions? Let me get out of here.